So up to last class, we have completed up to spherical capacitor. Start with some numericals of parallel plate capacitor. Start with question number 2.5. So parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. So the capacity is 8 into 10 raised to the power minus 12 farad. This is the capacity of capacitor. What will the capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6. So this is capacitance in air. Capacitance in air is epsilon naught A by D, which is 8 into 10 raised to the power minus 12. This is capacitance of a parallel plate capacitor. And the medium between the plates is air. Now, if I fill this parallel plate capacitor with some medium of dielectric constant K, then this would be K epsilon naught A divided by separation is half. They're asking about the value of, and K is 6. K is 6. So if capacitance in air is this 8 into 10 raised to power minus 12, then the capacitance in medium would be K epsilon naught A by D by 2. I can take this 2 in numerator. So capacity in medium is twice of K epsilon naught A by D. K epsilon naught A by D. Next, you can easily substitute the value of K. The value of K is 6. So it's 2 into 6 into epsilon naught A by D. Here, epsilon naught A by D is 8 into 10 raised to the power minus 12. So that's 12 into epsilon naught A by D. It's 8 into 10 raised to the power minus 12. So it's 12 into 8 into 10 raised to the power minus 12 farad. So this is the capacitance of parallel plate capacitor with a medium of dielectric constant K, and the space between them is half. So when you missed yesterday's lecture?
Yes, sir. So I have to go for hospital.
Okay, I have to go for hospital. So did you watch that lecture on YouTube?
I don't get our lecture. Yesterday when I checked, I got some medium in Hindi.
There is one playlist by the name of UAE and English lectures, and we are continuously sharing those lectures in your WhatsApp group also. We have updated this in the morning. So is it clear? Jimena, that lecture is updated in the WhatsApp group. So is it clear? This numerical 2.5.
Yes, sir.
Move on to the next one. Just try this question number 2.8. This one, 2.8. You have 2 minutes for this numerical. Just solve this numerical and report your answer in chat. Question number 2.8. So Jumena, here we are calculating capacitance. I'm writing the formula, all formulas. A capacitor have 2 conducting plates at some separation D. Area of each plate is A. If the medium between the plates is A, then the capacitance is epsilon naught A by D. If the medium between the plates is something else than A, the dielectric, so that's K epsilon naught A by D. If in this parallel plate capacitor, I introduce a dielectric slab K in some thickness T, then the capacitance will be its epsilon naught A over D minus T plus D by D. This is the capacitance on introducing a dielectric slab of thickness T.
So here T is time.
No, T is the thickness of the slab. The thickness of the dielectric slab.
K is the constant.
A, D, which one? K. Yeah, K is dielectric constant. K is dielectric constant. D is the separation between the plates. T is the thickness of this slab. And instead of a dielectric slab, if you put a conducting slab between the plates of capacitor, if it is a conductor, then the capacity is epsilon naught A over D minus T. And you can calculate charge using this relation, that charge is capacity into voltage, potential. So Afroza's answer is 1.771 into 10 raised to minus 9. Okay, Afroza, I'm just checking. Yes, Afroza, your answer is correct. Johanna, I got 2 farad. Johanna, you're making some mistakes. See, you have a parallel plate capacitor. Plate area is this, and separation is 3 mm. There's no information given about the medium between the plates. That means you can assume that medium between the plates is air. Air area is 6 into 10 raised to the power minus 3 meters square. And the separation between the plates is 3 into 10 raised to the power minus 3. Voltage is 100. If I substitute the values, D, which is 3 into 10 raised to the power minus. So it gets cancelled out. So this 3 will cancel this 2. And this C comes out to be 8.85 into, so this is 0, 7, 16.7 into 10 raised to the power minus 12 farad. 10, 16, 7, 1, 16, 17.7. 17.6 into 10 raised to the power minus 12 farad. This is the capacity. Now, once you have capacity, you can easily calculate the charge over the capacity. Q is simply CV. If you substitute the values, this is 17.6 into 10 raised power minus 12 into V, which is 100. The value of charge is 17.6 into 10 raised to the power minus 10. Is it clear now? Joanna, Afroza, Fatma? In the same question, in question number 2.8, now calculate 2.9. Calculate the capacity. In 2.9, first calculate the capacity. Part A and B I will solve, but you first calculate the capacity. What would be the capacity after introducing a mica sheet? Answers. You have introduced a dielectric sheet between the plates of capacitor. Supposed to calculate capacity. 105.6 farad, okay? It's not 105.6. Joanna, you're not doing unit conversion. It's not farad. Afroza is 1.06. Fatma, what's your answer? And Jubena. So now this is area, this is D. Okay, now let's take your calculation. And in between the plates of capacitor, we have introduced, the separation is D, this thickness is T. And the dielectric constant of the mica sheet is 6. So this is partially filled. So the expression will be epsilon naught A by D minus T plus T by T. Let's substitute the values. Epsilon naught is 8.85 into 10 raised to the power minus 12. Area is 6 into 10 raised to the power minus 3. T is 3 into 10 raised to the power minus 3. The thickness of the slab is, okay, and the separation is 3 mm. So this is not partially filled, this is fully filled, sorry. It is not partially filled, this is fully filled. This filled the whole space. Earlier too, the separation between the plates is 3 mm. And again, your dielectrics, the thickness of the dielectric slab is again 3 mm. That means your plate is fully filled between the plates. Your capacity will be K epsilon naught A by D. I guess the answer of first part should be same as that of 2.8. So K is 6. Epsilon naught is 8.85 into 10 raised to the power minus 12. Area is 6 into 10 raised to the power minus 3. Divided by D, which is 3 into 10 raised to the power minus 3. This gets cancelled out. This gets cancelled out. So the capacity comes out to be same. That's 12 into 8.85 into 10 raised to the power minus 2. So the capacity comes out to be, it's 8.85 into 12. 8.85 into 12 means 106.2. So 106.2 into 10 raised to the power minus 12. So this is the capacity. Is it clear? Now let's come to part A. He's asking what would happen if in the capacitor a mica sheet were inserted between the plates. The part A says while the voltage supply remains connected. If the voltage supply remains connected, that means voltage across the plates of capacitor is 100 volt. The capacity is 106.2 into 10 raised to the power minus 12 farad. You can easily calculate charge, that Q is equal to CV. Your charge will be 106.2 into 10 raised to the power minus 12 into 100. So charge comes out to be 106.2 into 10 raised to the power minus 10 coulomb. So this is the capacity, voltage and charge when the battery remains connected. If I just disconnect the battery, Fatma, does connecting or disconnecting battery affect capacitance? No. Capacity is independent of voltage and charge. So even if you disconnect the battery, capacity will not change. It will be 106.2 into 10 raised to the power minus 12 farad. But on disconnecting the battery, charge becomes constant. Remember this thing. Whenever you disconnect the battery, on disconnecting battery, charge becomes constant. On disconnecting battery, charge becomes constant. Constant means charge before the introduction of dielectric, means charge that we have calculated in section number 2.8. That is equal to before introducing dielectric. Before introducing dielectric. So see, earlier your capacitor have air in between the plates. Capacity was epsilon naught A by D. We have calculated charge using C. Then he inserted a dielectric slab between the plates of capacitor. But the battery is disconnected now. Once you have disconnected the battery, charge will become constant. Charge will become constant means the charge will remain same as per before the introduction of dielectric slab. Before introducing dielectric slab, the value of charge was we have calculated in the last section. What was the value of charge? What was the value of the section?
106.2 into 10 raised to minus 12.
Into 10 raised power minus 12 or minus 10 charge?
Minus 10 raised to minus 12.
Minus 12 was capacitance. Asking about charge.
Yeah, minus 10.
So the charge will remain same. Now you can calculate potential. Potential will be charge divided by capacity. So potential will be 106.2 into 10 raised to the power minus 10 divided by capacitance, where capacitance is this 106.2.
Sir, 106.2 was capacitance, right?
Yeah. I'm
This
asking
question.
charge in the last section. What was the value of charge?
17.6 into 10 raised to minus 10.
17.6. 10 raised power minus 10. So that's 17.6 into 10 raised power minus 10 divided by C, which is 106.2 into 10 raised power minus 12. So this way. So always remember, if your battery is connected, that means your voltage will remain constant. If battery is connected, that means your voltage will remain constant. And if you disconnected the battery, then charge becomes constant. Charge become constant means the value of charge will remain same before and after the introduction of that. Just note it down and let me know if you have any doubt in it. Okay, let's erase it. Now, after this parallel plate capacitor, the next thing is force between the plates of capacitors. Again, a question in NCERT. And the question says calculate force between the plates of capacitor. Between the plates of capacitor. So you're supposed to calculate force between the plates of capacitor. So see, you have two plates of capacitor. One having a positive charge plus Q, another having a charge minus Q, one having a charge density plus sigma, and another having a charge density minus. The separation between the plates is D. This D is the separation between them. So can I calculate? See, one is positive, another is negative. So they should attract each other. Can I calculate this force using Coulomb's law? Will the force be like this, Q into Q by D square? Yes. Can we calculate force in this way? Why not, Fatma? Why can't we calculate between them?
Because the formula is only for point charges.
Yes. We can't calculate force in this way because the formula, that is Coulomb's law, is valid only for point charges. If you have non-point charges, then you can't use Coulomb's law. Coulomb's law is valid only for point charges. For non-point charges, you can use this concept that force on a charge is charge multiplied by electric. You can use this relation. This is valid even for non-point charges. So first of all, we will calculate electric field due to the sheet, positive sheet. Let's calculate electric field due to this positive sheet, E plus. Let us calculate electric field due to positive sheet. Afroza, what is the value of electric field due to this positive sheet? Afroza, value of electric field due to one positive sheet. I used this many times yesterday. Answer. Joanna, value of electric field due to a positive sheet? No. Joanna, what should be the value of electric field due to the sheet, this positive sheet, one sheet? We have used this expression, right?
By epsilon 0 to epsilon 0.
Sigma by epsilon naught was for one sheet. Sorry, sigma by epsilon naught was for two sheets. If you have just a single sheet, then the electric field due to the single sheet is sigma by 2 epsilon. And in this electric field, a charge minus Q is placed. What should be the direction of force over this charge minus Q? In this electric field, E plus, we placed a negatively charged plate. In which direction did this negatively charged plate will experience force? It will experience force in opposite direction. This negative charge plate will experience force in a direction opposite to that of electric field. This will experience force in opposite direction. So the force will be QE. So the force is QE plus. If I consider this in vector form, this is minus of Q. But if I'm considering only the magnitude, then we can just remove this negative sign. This is F is equal to QE. Just keep on substituting the values. Q is Q, E plus is sigma by 2 epsilon. Fatma, what's the relation between sigma and Q? Fatma, relation between sigma and Q. Can you convert sigma in terms of charge? Afroza, relation between sigma and Q? Yes. Q by K. Sigma, it's Q by A. Sigma is charge upon area. It seems like you people haven't wake up yet. Huh? Sigma is charge upon area. Charge density. So the expression of force is Q square by 2A epsilon. This is again question of NCRT. F is Q square by 2A epsilon naught. This is the force with which the plates of capacitor will pull each other. Okay, let's erase it and move on to the next topic. The next topic is energy stored in capacitor. Energy stored in capacitor. So energy stored in capacitor. What is the cause of potential energy of Rosa? What is the cause of potential energy? You have a positively charged plate and a negatively charged. What is the cause of potential energy? No. The cause of potential energy is not charge transfer. This is how we calculate potential energy, but cause of potential energy. Fatma, what is the cause of potential energy? Cause of electric potential energy is electric force. Wherever you have electric forces acting on the system, that system will have some potential energy. We will calculate that potential energy through work done or through charge transfer, as you are saying. But the cause of potential energy is not charge transfer. Its cause is not work done. Its cause is electric force. Whenever you have electric force in a system, that system will have some net potential energy. You can calculate that potential energy through work. So you have a capacitor. The charge on one plate is plus Q. The charge on another plate is minus Q. So these positive and negative plates will interact with each other. Due to this interaction, the system will have some potential energy. That's the first step. In the next step, you're supposed to calculate this potential energy. To calculate this potential energy, let's consider initial state. The initial state of the system is, let's say I call this as the initial state of the system. Initially, your capacitor was uncharged. Initial means T equal to 0. Means there is no charge on the plate of capacitor. That's the initial state. Initially, no charge on plates. Initially, there is no charge on plates of capacitor. This is the initial state. In the final stage, let's say at some final stage T equal to capital T, your capacitor is fully charged. Capacitor is fully charged. Means the charge on the plates is plus Q and minus Q. This is the final stage when your capacitor is fully charged. This is plus Q, minus Q. Finally, the charge on the plates of capacitor is Q. Finally, the charge on plates is Q, and potential difference between plates, the potential difference between the plates is V. This is the final stage. So we have to calculate the work done in charging this capacitor from initial, means when charge is 0, to the final state, means charge on the plates is capital. So work done, we have to calculate work done to charge this capacitor. To calculate this work done, we consider a state in between 0 and capital T, intermediate state when charge on capacitor is, let's say, Q prime, and potential difference between plates is V prime. Potential difference between plates, when the charge on capacitor is Q prime, and potential difference between the plates of capacitor is V prime. We are considering an intermediate state. So this is the plates of capacitor at some time instant t equal to t, when the charge on plate is plus Q prime and minus Q prime, and the potential difference between the plates is V prime. This is parallel plate capacitor. So this is initial stage when your capacitor is uncharged. This is your final state when your capacitor is fully charged. We have considered an intermediate state when the charge on the capacitor is Q prime and potential difference between the plates is V prime. Next, we will calculate work done in bringing 0 to Q charge on the plates of capacitor. First, note it down. Yes, Jumena, we will calculate energy through work done using the same method through which we have calculated potential energy of 2-point charges and n-point charges. We will calculate it through work. I'm just coming to it. To calculate work done, these three states should be very clear. That's the initial stage, that's the final stage, and this one is the intermediate stage. So the charge on the plates at some t equal to t is Q prime. I want to transfer an additional charge, work done, to transfer some dq prime charge to the capacitor. So if potential difference between the plates is V prime, so how would you calculate work done to transfer dq prime charge? Do you remember any relation between work done charge and potential difference? It's an open question for all. Do you remember any relation between charge, potential difference, and work done? No one remember. Do you remember this relation, work done from A to B is charge potential at B minus potential at A? We have used this relation many times. We have used this relation to derive potential energy of 2-point charges, n-point charges. You remember this relation? Okay. So now can you calculate work done here? This dw prime work done? If you remember this expression, then you can easily calculate work done. So what should be the work done in carrying this dq prime charge from one plate to another? The potential difference between the plates is V prime. Now for the P cross, no. Work done. This is charge into potential difference. The potential difference between the plates is V prime. The charge is dq prime. Fatma, what should be the work done? Now I need answer of each one of you. Afroza, you are wrong. Fatma, what is the work done in carrying dq prime charge to the plates of capacitor when potential difference between the plates is V prime? You can refer this formula. R. Why R? No. Jovena, how do you calculate work done?
Q dash by 4 pi epsilon.
No. The last one is Johanna. Johanna, how do you calculate work done? You have charge, you have potential difference.
Prime into V prime.
Yeah. EQ prime into V prime. It's simple. Now, work done is charge into potential difference. You are carrying dq prime charge. Potential difference between the plates is V prime only. So the work done is dq prime into V prime. Is it clear? Fatma, Afroza, Jumaina, you all were wrong. Is it clear now? It's charge into potential difference. Say, this is my equation number 1. Okay, next. If C is capacitance of capacitor, if C is capacitance, now this capacitance is independent of charge and potential. If C is capacitance, then I can write this C, or I can write this Q prime as CV prime, and we can write V prime as Q prime by C. That's equation number 2. Instead of this V prime, we can substitute this thing. Let's substitute 2 in 1. So the work done in transferring dq prime charge to the plates of capacitor, it's Q prime by C. This is work done for the small amount of charge dq. We need to calculate work done from initial to final stage. That means work done to transfer 0 to Q charge on plates of capacitor. So we need work done to transfer 0 to Q charge on plates of capacitor. That work done will be integral of Q prime by C dq prime. Okay, can you people guess the limits of this integral? The limits of integral, just the lower limit and upper limit. Yes, the lower limit is 0 and the upper limit is capital. This is the limit. So is it clear up to this step? See, you don't have to memorize the derivation. You should know the reason for each and every step, why we are using this particular step. Because to calculate potential energy, the only method is through work done. Potential energy, we always calculate potential energy through work done in carrying your system from initial to final stage. In the initial stage, charge is 0. In the final stage, your charge is capital Q. So this is how we calculate work done. The next, you can write your work done as, you can take 1 by C outside. It's 0 to capital Q. It's Q prime dQ prime. Next, you can take your work done as 1 by C. It's Q prime square over 2. Limit is from 0 to capital. It's 1 by 2C. It's Q square minus 0 square. So work done is Q square by 2C. This work done gets stored in the system in the form of potential energy. This work done gets stored in system in form of potential energy. So you can write your potential energy as your potential energy is equal to work done, which is Q square over 2C. This is how we calculate potential energies. Work done, which is Q square by 2C. Next, we can convert this expression of potential energy, which is in terms of charge and capacitance, in terms of potential and capacitance. You can substitute Q is equal to CV. If I substitute Q is equal to CV here, then this is C square, V square over 2C. This gets cancelled out. So this is half CV square. So this is how we calculate potential energy, which is half CV square. Just note it down, then we'll do the next. Okay, next we can convert this expression of energy in terms of charge and potential now. We can as well remove capacitance from this equation. We can write C as Q by V. So your energy comes out to be half. It's Q by V into V square. Square will cancel this V. Your energy will comes out to be half. So this is how we calculate potential energy of capacitors, half Q. This is the expression of potential energy of capacitor, which is half Q. So you should remember these three formulas: Q square by 2C, half CV square, or half Q. All three for potential. So can I erase it? So I'm erasing it. The next thing is energy density. This is again a question of NCERT. It says calculate energy density of parallel plate capacitor. Calculate energy density for a parallel plate capacitor. Parallel plate capacitor. So say you have a parallel plate capacitor. The plate area is A. The separation between the plates is small. So here energy density means energy per unit volume. Energy density means it's energy per unit volume. Energy density is energy divided by volume. We represent energy density by small u, energy by capital U, and volume by V. This is first equation. Jubena, what is the volume of this capacitor? Area and separation are given. What is the volume of this capacitor? Yes. What is the volume of this capacitor? No answer. Fatma, volume of this capacitor? No. Volume. Afroza, Johanna, what's volume of this capacitor? You can easily calculate volume. It's area into separation, not AQ. It would be AQ if it were a cube. If you have area of cross section and separation, then the volume is simply area of cross section multiplied by separation. So volume is simply A into D. So this is the volume of capacitor, which is A into D. That is second equation. You can substitute 2 in 1. When we substitute 2 in 1, so energy density is energy. Fatma, D is the separation between the plates, right? A is the area of plate and D is the separation of plate. So the volume of the entire capacitor is A into D. And you can write your U as half Q square over C. This is energy, half Q square over C. If I substitute 2 and 3 in 1, then U is, it's half Q square over C divided by volume, which is A into D. So this is the energy density, which is Q square over 2C into area into separation between the plates. Next, we can write your capacity is epsilon naught A by D. This is the expression of capacity. So your energy density comes out to be, it's Q square by 2 epsilon naught A by D into A into D. You can just cancel this D with this D, and energy density comes out to be Q square by 2 epsilon naught A square. What is Q by A? Charge upon area. What is charge upon area? Q by A. Afroza. Sigma. Q by A is charge upon area. Sigma, charge density. Q by A is sigma, which is charge density. Instead of this Q by A, we can write sigma here. So your U is sigma square by 2 epsilon. If I multiply it with epsilon naught with numerator and denominator, this comes out to be half epsilon naught sigma square by epsilon naught square. What is the expression of electric field between the plates of capacitor? So this is equation number 4. Expression of field, electric field between the plates of capacitor. Electric field between capacitors. What's the expression of field?
Q square by 2E.
Field is sigma by epsilon, right? This was the expression of field between the plates of capacitor. This is 5. If I substitute 5 in 4, so energy density will be half epsilon naught E square. This is the energy density between the plates of capacitor, half epsilon naught E square. This is the desired result. Any doubts in this calculation?